Okay, this is class number 25, Street Reading Problems and Graphs, Part 2, and it goes with sections 5.3 and 5.4. All right, our daily summary. In this lesson, we're going to take a look at Euler's theorems, Flurries algorithm, and optimal and semi-optimal Eulerizations. All right, in today's demo, first thing we're going to do is determine whether each of the following graphs has an Euler path, an Euler circuit, or neither. And so a reminder here, an Euler path is a path that covers all the edges of the graph once and only once. An Euler circuit is a circuit that covers all the edges of the graph once and only once. Right, so a hint, try tracing all the edges of each graph without lifting your pen or pencil. Remember, you don't have to finish in the same place that you started for a path. So you may want to press pause, give these 6 graphs a try, experiment a little bit with them. And again, mark which ones you found an Euler path in, which ones have an Euler circuit, and which ones have neither. Okay. So I've labeled them with their answers. So you can see the one on the top left is an Euler circuit, which means you can go around all the path, or all the edges rather, and start and stop in the same place. This one on the lower left, for example, has an Euler path. So if I start down at Z, I can trace over all the edges and end up back at Y, a different place. This one in the middle doesn't have either. Over on the right has an Euler path, and I'll give you an example of that, but it may be different than the one you found. And so we may have gone up, down, over, back up, and then around those multiple edges. And so we would finish or end at A. Okay, in the middle on the bottom has an Euler circuit, and again, just to give you an example of one which may not match what you had. Here's one possibility. And notice that I start and stop in the same place. So my start and my finish are vertex C for this example. And then on the bottom right, that might look familiar to you. That's the bridges at Königsberg, and that doesn't have either an Euler circuit or an Euler path. All right, so number 2, what do the graphs that have an Euler path have in common? So we're going to look at the degree of each vertex. And what do the graphs that have an Euler circuit have in common? So again, we want to look at the degree of each vertex. So we come back up here. Remember, degree was how many edges go into a vertex. So it has degree 2, 2, and 2. This one has 1, 2, and 2. And you may want to press pause and try these out, and press play when you're ready. Oops, that one has degree 3, 4, and 2. And I think I missed one. Let's see. Nope, this has degree 4 down here. Right, on the top in the middle, we've got degree 2 on all those corners and degree 3 on those middle ones. And then on the inside, it looks like these are all degree 3 as well. Right, over on the right, we have degree 3, 1, 2, 3, 4, 5, degree 5, degree 3, and degree 3. And then on the top right, we've got 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, and 2. All right, so if we look at the ones with an Euler circuit, so this one and this one, if you look at the degrees of all those vertices, notice that they're all even numbers. Right, so I think that's our number 3, all even degree. All the vertices have an even degree. Right, so let's take a closer look at the ones with the paths or Euler paths. So we've got the bottom left one here. And notice it does have an even degree in there. Here's our other Euler path. And they both have some vertices with an even degree, but notice they each have an odd degree. And I did make a mistake here. You probably caught this already, but that had a degree 3. So in fact, on closer look, this one has 2 odd degree vertices. Top right, 2 odd degree vertices. Right, so if we found the pattern, it looks like they have 2 vertices that are odd degree, or that have an odd degree. And if we look at the ones that have neither an Euler path or an Euler circuit, so this is number 4, what do they have in common? And again, the hint is to look at those degrees. So those 2 remaining graphs, here's one with neither an Euler path nor an Euler circuit. Here's the other one. Notice they have more than 2 odd degrees. In fact, this one at the bottom, all the vertices have an odd degree. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 odd degree vertices, and looks like 5 even degree vertices. So how they're different from the other two, from the Euler path and the Euler circuit, they have more than 2 odd degree vertices. Okay, so we just discovered some of Euler's theorems. First one, Euler's circuit theorem. If a graph is connected and every vertex is even, then the graph has at least one Euler circuit. If a graph has any odd vertices, then it doesn't have an Euler circuit. Euler's path theorem. If a graph is connected and has exactly 2 odd vertices, then it has at least one Euler path. Note that any such path must start and stop, or must start at one of the odd vertices and end at the other odd vertex. We'll go back, we'll double check that when we return to the previous page. And then C, Euler's sum of degrees theorem. The sum of the degrees of all the vertices of a graph equals twice the number of edges, and therefore is an even number. A graph always has an even number of odd vertices. All right, so number 6 and number 7, we're going to go back to the previous page. We're going to see if we can figure out how these theorems work. All right, so let's take a look at the Euler circuit one. And keep in mind that if you have a vertex with an even degree, so I'm going to look at vertex F down here, it means if you come into that vertex, you're also going to be able to leave it. So if you think about where you started and stopped, if you come out or leave that vertex, at some point you're going to be able to come back in and end up there. Versus an odd degree vertex, let's look at an Euler path. Here's an example of that down here. If you have an odd degree, you're going to be able to leave that. It's degree 1, you're never coming back to it, so it rules out a circuit. You look at the other odd degree vertex, you can come in, you can leave, and then you're going to end up coming back in and getting stuck there. So it's going to be your ending point. And so those two theorems help us out in identifying which graphs have Euler paths and which ones have Euler circuits. And then that third theorem, we'll go back to the other screen, we can write this in over here. So how does the third theorem work? Well, keep in mind that an edge is what connects 2 vertices. And it may be the same vertex, because it has to start and stop at a vertex. But if you look at that, then each end of an edge is going to contribute 1 degree to your total. Right? So that means you're going to have 2 times the number of edges. That's going to give you the number of degrees in your graph. Right, so let's check that out. Let's pick out a graph and see if that works. All right, let's start with the top right one. So notice if we add up all our degrees, we get a total of 6. And we have 3 edges. So if we do 3 times 2, we also get 6. And I encourage you to try this out with one other graph just to verify this. Also keep in mind that other part of Euler's sum of degrees theorem says that a graph also has to have or always has an even number of odd vertices. So let's check. In this graph, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 odd degree vertices. So they're even, an even number of odd degree vertices. And if you check this out with another graph, you'll find the same is true. Okay, so number 8, how do we find an Euler path or circuit once we know that the graph contains one? Well, many of us are going to be able to find these paths and circuits through simple trial and error. And the ones, or the 2 that are below, I want you to use trial and error to find an Euler circuit for the graph on the left, an Euler path for the graph on the right. And these are the graphs you saw on the previous page, so you may have already done this. Right? But if you didn't, press pause, try it again. And the graph on the left, here's one example of an Euler circuit. Keep in mind that we could just as easily have done this. I didn't draw my vertices back in, but I can start and stop in the same place, go a different direction. I could also start down at vertex E, go to the right, then up, and then back down. So there's a bunch of different circuits that are possible. And then in the one on the right, here's one example of a path. But again, just like before, we can change that up a little bit. Some of you may have started here and done that, come down, and then finished where I started. Okay, so notice that's just trial and error. We weren't using anything else. Right, so 9, important question, what if trial and error doesn't work? What if you get stuck? So if you run into trouble, there's an algorithm that can help. By the way, an algorithm is just a set of procedural rules that, when followed, are going to lead to a solution. So it's guaranteed to get you to a solution. Right, Flurries' algorithm does that. It gives you a way to find an Euler circuit and Euler path if you get stuck. Right, so your first step, you want to make sure that the graph is connected. And either one has no odd vertices if you want an Euler circuit, or 2 has just 2 odd vertices if you want an Euler path. Right, number 2, you got to choose a place to start. So that can be any vertex if you're doing a circuit, but it must be one of the 2 odd vertices for the path. Right, step 3, at each step, if you have a choice, don't choose a bridge of the yet to be traveled part of the graph. However, if you have only one choice, take it. And we'll get an example of what this means on the next page. And number 4, when you can't travel anymore, your circuit or your path is going to be complete. Okay, number 10, we're going to use Flurries' algorithm to find an Euler path for the following graph. So I'm going to start with the one on the left. And again, if you want to press pause and try this out, you can. First up, let's look at the degrees of each vertex. That's how many edges go into that vertex. And that's important because an Euler path is going to have to start and stop at these odd degrees. So vertex A either has to be our starting point or a finish point, and Y needs to be the other one. So I'm going to start down here at Y. I'm going to go up this. So I'm going to label these in the order that I go in. I'm going 1, and then this cross one I'm going to do is my second edge in the path. And then I'm going to go across, up, and then I can do these last 2. And notice I am ending up at that other odd degree. So this was my start, and this was my end or finish. All right, so I didn't really use Flurries' algorithm there, but I wanted to give you an example of what they meant by the bridge, not crossing a bridge. All right, so let's say that I do start here. Yeah, no, actually, let's start up here just as an example. So here's my start. If I come down here and this is my first edge that I travel, let's say I go up here as my second edge, and I come down here for my third edge. What I don't want to do is go down here. So notice that I'm getting stuck because once I get to Y, there's not going to be any place for me to go. So this is what Flurries' algorithm refers to as a bridge of the untraveled part. So note that I can't use this edge. I can't do this. Okay. Edge XY is a bridge at this point. Okay, even without the algorithm, you may get there and go, I'm stuck. Let me undo 4. Let me come back and switch, do these 2 next, and then finish up with that as number 6. All right, the one on the right, I'm going to put an example in. I encourage you to press pause and try this out on your own. Okay, so I started this one. I identified the even degree vertices and the odd degree vertices. And I found that those 2 on the sides are the odd degree vertices, so they're going to be my start and end. And then if you want to trace through where I've already been, note that I started here with 1, went up across the top, down on the diagonal, cross to the right, up to the right, down, up the diagonal, down again, across, and down this diagonal. I'm stopping right there because I want to point out that I can't use this edge right now because that, again, according to the algorithm, is a bridge for the untraveled part. So instead, I'm going to go in the other direction. I'm going to go up for 13, over for 14, 15, 16, 17, 18, 19, and now I can use those last 2 edges, 20 and 21. All right, so number 11, we're going to do the same thing. We're going to use Flurries' algorithm to find an Euler circuit for the following graphs. So if it's an Euler circuit, they should all be even degree. So it looks like we have all even degrees over here. Right. Then we can start and stop anywhere we want. So here's one possibility. Again, if you press pause to try this out on your own, you may have a different circuit. And Flurries' algorithm still applies here. So if you get stuck, it may be that you used a bridge for the untraveled part, and you just need to backtrack and try again. All right, so here's one example of a circuit. I'm going to start at E. So notice I don't want to do C to E next because that's going to cut off part of this bridge or part of this graph. So I should have 9 as an ending point. All right, so question 12 or number 12, what do we do if we need an Euler path or circuit, but our graph doesn't meet the requirements given in Euler's theorems? Remember, the goal of most street routing problems is to find a route, either a path or a circuit, that covers all the edges of the graph while recrossing the fewest number of edges, and that's in hopes of saving some time or some money. And the solution to our problem involves turning some odd vertices into even vertices by adding duplicate edges in strategic places, and this process is referred to as Eulerizing if we're doing circuits, or semi-Eulerizing if we're doing paths. So we're either Eulerizing the graph or we're semi-Eulerizing the graph. These duplicate edges are going to indicate which edges will need to be recrossed or traveled down a second time. All right, so number 13, the following graph does not contain an Euler circuit. Okay, so if we wanted to put one in, we wouldn't be able to. And notice that the problem lies here, and here we've got 2 odd degree vertices. The rest, by the way, are even. They're all degree 2. All right, so down below, each of the following shows the route that I took through the above graph to complete my Euler circuit. The dashed lines indicate edges that were traveled along twice. And note each circuit starts at vertex D, and the edges are numbered in the order in which they were traveled. So for instance, this one on the left, I started at D. I went down this direction, up, across this dashed line. So it meant I used edge BC a second time. Then I went up, I went across, up, down, and across. So I ended up back where I started, so that was good. If you look at the other 2, something very similar. I went down this edge, across. I used that edge a second time. That's what that dashed line indicates. And then went up, continued going up, went down. I used that edge a second time. That's what that dashed line is for. Doubled that edge, used it a second time, and then I finished there. Over here on the right, still starting at D, I went down, up and over again, down, down, and then I had to repeat that edge. So again, that dashed line says I'm using edge EC a second time, and then I was able to finish at D. Right, so which graph does not follow the rules of the road? Right, notice that graph 1 doesn't. And you may have caught this when I was showing you my route through that graph. But graph number 1, the one on the left, note that edge EB, and grab a different color marker, that's this edge right here, is not in the original graph. So I can't just make up roads when I'm doing this. There was no street there, no bridge there. So if you think about the Koenigsberg Bridge problem, it's like swimming across the river, just making my own spot to go. If you think of a street map, it means I'm driving through the park or maybe through the school, but it's not a possibility. If there's no edge there, I can't create one. All right, and the second question, which one seems the best or the optimal route? Well, graphs 2 and 3 at least follow the rules of the road, but notice that graph 3, the one on the right, only took 7 edges. Graph 2 in the middle took 9. So in terms of time and money, graph 3 is probably going to be the better option because it had the fewest duplicate edges. And again, graph number 3 is the one on the right. Oops. And graph number 1, by the way, was on the left. Okay, so 14, now that we have an idea of what an optimal Eulerization looks like, how do we go about finding one? Well, the following graph represents a street grid. We would like to find an optimal route that covers all of the blocks of the street grid and ends back at the starting point. So it would be an Euler circuit. So let's take a look at the process involved in finding an optimal Eulerization for this graph. And by the way, in this case, your vertices are representing intersections on that street map. So where roads cross, and the edges are representing the roads themselves. Okay, well, your first step, you've got to identify the odd vertices. So if we go through this graph, I'm just going to write the degree next to each vertex. Remember, the odd ones are the problem if we want to do a circuit. That's why we want to identify those before we do anything else. And these ones in the middle, notice, have degree 4. All right, so that's your first step. Second step, we want to add a duplicate copy of the edges that will make these vertices even. There are many ways to do this, but our goal is to add as few duplicate edges as possible. And note, you can only duplicate edges that are part of the original graph. All right, so one possibility, I could duplicate edge LK, and that again indicates we're going to use that edge twice. Duplicate that one, duplicate this one, and duplicate that one. And now if you take a closer look, and we'll do this for vertex F as our example, there's 1, 2, 3, 4 edges going into that vertex. So we've succeeded in making that even. And in fact, that's true of all of these odd degree vertices. We just made them all even. Oops, should cross out the degree by adding those duplicate edges. Okay, so number 3, note that the resulting graph is called an Eulerization of the original graph. This Eulerized version of the graph has all even vertices. If you complete the Eulerization with the fewest possible duplicate edges, then you have what we call an optimal Eulerization. All right, so there are extra copies of this graph below, so if you want to try it out on your own, you can. But I'm going to use the one on the left to show you an Eulerization that's not optimal. So I'm going to put not optimal. All right, so remember that B and C, E and F, H and I, and K and L were all your odd degree vertices. So here would be an example of an Eulerization that's not optimal. And the reason for that, if you look more closely, notice that I had to add, got 1, 2, 3, 4, 5, 6, 7, 8 edges that are going to get repeated or duplicated, versus what we did up above only required 4 extra edges or 4 duplicate edges. So again, optimal, we want to do it as few extra edges as possible.